take care of this first. Okay, so this is where we stopped, and I started by saying that it's a weak acid. I'm going to use, or I did use HA to represent the formula for the weak acid. And we know that weak acids undergo partial dissociation to form, in this case, H plus and A minus. And I set up an ice table where initially we had 0.065 M of the acid initially. Initially, you'd have no hydrogen ions or A minus. And I remember saying that we let X be equal to change in the concentration of HA, right? Because we don't know how much of it reacted. So here I'm going to put minus X, which means that according to the stoichiometry of the equation, this would be plus X in terms of the change in the concentration of H plus and plus X also in the case of A minus, so that at equilibrium, we're going to have 0.065 minus X. Here we're going to have X for the concentration of H plus and X for the concentration of A minus. Now, we can write down the equilibrium expression for the dissociation of the weak acid, which is Ka is equal to the concentration of H plus times the concentration of A minus, all divided by the concentration of HA. And then what we do at this stage is to put each of these terms in their respective places in this equation, right? So this becomes X squared over 0.065 minus X, all right? Now, this is where we stopped the last time. Now, oh, by the way, Ka is given. Ka is equal to 1.8 times 10. Easier, what we can do is make an assumption, right? And this assumption is based on the fact that the acid is weak, right? And the assumption is this. Assumption we're making is that the size of X is so small that it is much less. I don't know if you're familiar with this symbolism here. It's two less than equal signs back to back. What this means is that X is much less than 0.065, right? Such that X, I'm sorry, 0.065 minus X is approximately equal to 0.065, right? So essentially what we're saying here is that we're assuming that X is so small compared to 0.065 that X is effectively zero compared to 0.065, right? So if we make that assumption, then this X here will drop from this expression. So this reduces to X squared over 0.065, and that is equal, excuse me, and that is equal to 1.8 times 10 to the minus 4. And this makes this equation easier to solve. So basically X would be equal to the square root of 0.065 multiplied by 1.8 times 10 to the minus 4. And then we do our number crunching. Let's see what this gives. So 0.065 times 1.8 times 10 to the minus 4. And then we find the square root of that. And according to my calculation, this works out to be equal to, rounded out to 2 sig figs, 3.4 times 10 to the minus 3. All right? So that's what we're saying X is equal to based on the assumption. Am I in your way?
A little bit, it's okay.
I'm sorry.
That's fine.
Okay, that's fine?
Yes.
Okay, so based on the assumption that we made here, we come to the conclusion that X is equal to the value of 3.4 times 10 to the minus 3. And therefore, since we're trying to find the pH, we can say that this is equal to the concentration of H plus. Now, we made an assumption because we made an assumption, we have to make sure that the assumption that we made is valid. And I discussed this in the video. We have to assume, or we have to test the validity of the assumption that we made, right? And how do we test it? We test it by determining what is called the percent dissociation of the acid. And the percent dissociation is equal to the concentration of H plus at equilibrium divided by the concentration of HA initially, right? Times 100%, okay? And basically, once we calculate that percent dissociation, if the percent dissociation is less than 5%, then the assumption that we made will be valid. So let's see if that's the case. So the concentration of H plus at equilibrium is what we calculated here, which is 3.4 times 10 to the minus 3 m divided by the concentration of the original concentration of the acid, which is 0.065 m times 100%. So let's see what that gives. So 3.4 times 10 to the minus 3 divided by 0.065 times 100%. And this turns out to be 5.2%, which is greater than 5%, which is the criteria that we use to determine whether or not the assumption is valid. So what does that mean? That means that the assumption that we made earlier is not valid. Assumption is not valid. So that means we have to come back to this equation here and solve it the longer way, all right? So because I need space, I have to do some erasure here. So let me, let me clear everything. Any questions so far before I erase this? Any questions? Any questions out there in Zoom?
Where would you get the 5% from?
It's a criteria that is, when it comes to solving these problems, it's a criteria that is established and recognized, basically. We say that, okay, if the percent dissociation is less than 5%, then the assumption is valid, and we can just go ahead using the value of X based on that assumption, right? But now that we have determined that the assumption is not valid, that means that we can go ahead with that assumption, all right? Okay, is it okay for me to clear all this? All right, so let me clear this. So what I'm going to do now is go back to this equation right here, which is 1.8 times 10 to the minus 4 is equal to x squared over 0.065 minus x, all right? So basically we have to go the longer route, which basically means that we're going to end up with a quadratic equation. And I've done that earlier. I'm just going to skip a couple of steps here and just get to the actual quadratic equation, which turns out to be x squared plus 1.8 times 10 to the minus x. I'm sorry, 10 to the minus 4x minus 1.2 times 10 to the minus 5 equals 0. And then when you solve for x, you get two possible values. One of them would be 0.0034, and the other one would be minus 0.0036. And between these two, this one would not work in reality because X cannot be negative, right? X would be the concentration of H plus, and you can't have a negative concentration. So therefore, this is the value that we're going to use. So therefore, we're going to say concentration of H plus is equal to, actually the same thing as we calculated earlier, 3.4 times 10 to the minus 3. Therefore, the pH is equal to minus log of 3.4 times 10 to the minus 3. So it turns out in this case, it doesn't matter if you use the assumed value, would be the same as the actual value that is calculated going the longer route. Anyway, so 3.4 times 10 to the minus 3, we find the log of that and the negative, and I got 2.47 as the final answer. All right. I don't recall saying this. I may have said so in the video that I've posted. But for your calculation of this type where you're given a, or you derive a quadratic equation, I will allow for you to use your fancy calculators. I know that, which calculator is it? TI, I don't remember which one. There's one of these fancy calculators that you can actually program to solve for quadratic equations. After you program it, all you have to do is put in the A, B, and C values, and then hit enter or execute or whatever, and it gives you the two possible values, right? So I have no problems with you guys using those calculators, because as you can imagine, if you were to actually use the quadratic formula, that will be, a bit lengthy, especially during a test. As you can imagine, that can be something that might take up too much of your time. So if you have one of those fancy calculators, and in fact, if I'm not mistaken, I think I've posted a video, let me just check here, in the module section. Oh no, wait a minute, is it announcements? Let me see here. I'll have to look for that video. I saw a YouTube video. And I remember in the past I've posted it. Let's see here. Let me check the modules if I still have it there. I'll just publish it if it is there. Okay, I'm going to see if I can find it, but basically it's an instruction type video, which basically shows you how to program your calculator to do that. So that all you have to do is plug in the A, B, and C values for the quadratic equation, and then you get your two X values. And that would save a lot of time, especially when you're doing your tests. If you have to solve for the quadratic equation like this one. All right, any questions about this? Any questions? Any questions? Okay, let me do this. All right, so let me clear this. And scroll down. Okay, so for question 9, basically you're going to compare the pH of these two. So basically you're going to say which one is higher or lower. I can tell just by looking that the one that would be lower in value is the nitric acid, because they both have the same molarity, and I know that nitric acid is a strong acid, and nitrous acid is a weak acid, which has a Ka value of 4.5 times 10 to the minus 5. So I can tell just by looking that the nitric acid would have a lower pH because it's a stronger acid. However, what you need to do is calculate the pH of both of them, right? Keeping in mind that the nitric acid is a strong acid and the nitrous acid is a weak acid. So if you understood what we did earlier, let me check earlier here. Earlier, you were asked to calculate the pH of, let's say, this acid right here, which is strong, right? That's basically the same process that you're going to apply to determining the pH of the nitric acid. And then as far as the pH of the nitrous acid is concerned, you're going to use the same method as we used in question number 8. All right? So the reason I'm telling you all that is because I'm going to leave you to try that on your own. All right? You're going to calculate the pH of both acids, the nitrous and the nitric acid, and say which one would be lower. Like I said, I already know that the nitric acid will be lower in terms of the pH compared to the nitrous acid. But that's what you're going to do, right? So the same method that I used in the previous questions, you're going to use those methods to answer question 9A, and I think the same is true for, or something similar for question 9B. In fact, hold on, let me check something here. Okay, I think I'm going to do B for you because we did not do a pH of a basic solution that is weak. All right, so in the case of B, potassium hydroxide is a strong base, ammonium hydroxide is a weak base, right? So for the potassium hydroxide, that's very easy because potassium hydroxide is strong. It will undergo complete dissociation to form potassium and hydroxide ions. So therefore, what that means is that the concentration of the hydroxide ions in this solution would be the same as the initial concentration of the potassium hydroxide, which is 0.02 m, which means that the POH is equal to minus log of 0.02. So let me see what that gives, 0.02 minus log. So according to my calculation, this works out to be equal to 1.7. All right, 1.7 would be the pH of the potassium hydroxide. Now for the ammonium hydroxide, that will dissociate to form NH4 plus and OH minus. Oh, by the way, did I tell you guys about the tables which gives you the dissociation constants for weak acids and weak bases? Did I? I guess not. Okay, so I probably mentioned it in the videos. So they gave you the Kb value for the base for the ammonium hydroxide, but you could be given a question where they don't give you that because you will have this table to look at. So let me show you what I'm talking about here. So if I go to tables, and then I go to dissociation constants, you will end up with this table I'm about to download. So this table here, if you can't ignore what I wrote, basically gives you a list of weak acids and their Ka values, right? And then there's a shorter list of bases and their Kb values, all right? So you will have access to this. Whenever if I give a test in the testing center, I will provide this table for you so that you can refer to it if you need it, all right? So I just remembered about this. I didn't remember if I told you guys about that. Anyway, so going back to the question. So the question, at this stage, we'll be determining the the pH of the ammonium hydroxide. So let me turn this on. So in this case, we're going to set up a nice table similar to what we did for the weak acid. Initially, we would have 0.10, and then here you'd have 0 and 0. The change here would be minus x, and plus x. And then at equilibrium, you're going to have 0.10 minus x. Here you're going to have x. Here you're going to have x. Kb, in this case, would be equal to the concentration of NH4 plus times the concentration of OH minus over the concentration of NH4OH, right? And then we plug in these terms into that equation like we did before. You're going to end up with x squared over 0.10 minus x, and that would be equal to 1.8 times 10 to the minus 5, right? And just like we did before, we would assume that x is much smaller than 0.10, which means that this part here becomes reduced to x squared over 0.10 is equal to 1.8 times 10 to the minus 5, which means that x will be equal to the square root of 0.10 times 1.8 times 10 to the minus 5. And let's see what that gives. So that's 0.1 times 1.8 times 10 to the minus 5. And then square root. So according to my calculation, oh, I didn't realize this was in the way. So according to my calculation, when rounded off to 2 sig figs, this becomes 1.3. Come on. 1.3 times 10 to the minus 3. All right? So now we again check to make sure. I'm going to do it up here. I'm going to determine the percent dissociation. And remember, the percent dissociation would be equal to the concentration of the base this time, the OH minus, concentration of OH minus, divided by the concentration of NH4OH initially. So this will be initial, this will be at equilibrium times 100%. And then I put the numbers in, so that would be 1.3 times 10 to the minus 4 m divided by 1.8 times 10 to the minus 5 m. What am I doing? 0.10 m. 0.10 m, that's what should be done here. 0.10 m times 100%. So let's see what that gives. 1.3 times 10 to the minus 4 divided by 0.1 times 100%. So that gives, according to my calculation, 0.13%, which is obviously less than 5%, which means that the assumption is valid. All right? So what does that mean? That means that we can take this to be equal to the concentration of OH minus. So I'm going to do that down here. So therefore, X is equal to the concentration of OH minus, which is equal to 1.3 times 10 to the minus 4. Right? M. Now remember, the question is asking for the pH. Right? So how would you, oh shoot, I just realized something. But anyway, I'll get to that later on. How would you find the pH if you have the concentration of OH minus? What's the relationship, or let me ask you this. What's the relationship between pH and pOH?
It'd be 14 minus the value.
I'm sorry, what's that?
It would be, for the one above, you would do 14 minus 1.7. Right.
Yes, that was what I realized I made that mistake. I should have calculated the pH. The pH is equal to 14.00 minus 1.7. So 14 minus 1.7. So that should be 12.3. Yeah, that's what I forgot to do here. 12.3. All right, so that's the answer for the potassium hydroxide. So how do we do the same for the ammonium hydroxide? I'm running out of space here. Let me just erase some stuff here. Let me erase. Okay, let me do this.
For the 1.3 value used in the percent dissociation, wasn't it 1.3 times 10 to the minus 3, or was it minus 4? Because I thought we got minus 3 from the
Okay, let
original.
me do it again. You could be right. 0.1 times 1.8 times 10 to the minus 6 times 0.1, and then I find the square root of that. No, it should be one. It should be to the 10 to the minus 4 actually.
Okay, because I thought it was 1.8 times 10 to the minus 5, not minus 6.
Oh, that's a mistake I made. Okay, thank you. So this should be minus 5. So this should be 10 to the minus 5. And then let me see here. 0.1 times 1.8 times 10 to the minus 5. And then I find the square root of that. So this should be 10 to the minus 3. Okay, so which means that up here, this should be 10 to the minus 3. So let me put that, make that correction up here. So let's see what that gives. Divided by 0.1 times 100. Okay, so it doesn't change things in terms of the assumption being valid, because what I calculated here would be 1.3%, which is still less than 5%, right? So we can still go ahead with the concentration. Let me draw a line here. So we can still go ahead and say that the concentration of OH minus is equal to 1.3 times 10 to the minus 3. All right? M. Okay, so how do we find the pH from here? How do we find the pH from this value for the concentration of hydroxide?
You find pH first.
Find the pH first, right? So pH will be equal to minus log of 1.3 times 10 to the minus 3. So let me see what that gives. 1.3 times 10 to the minus 3 log. So I got 2.89, right? And then what? Now that we have the pH, then we do what?
The pH would be 14 minus.
Exactly, we find the pH. So the pH will be equal to 14.00 minus 2.89. So let's see what that gives. So according to my calculation, this works out to be equal to 11.11. Let me see if I got that right. Yeah, I think that's right. I don't know what I have here. Oh, okay, I realize a mistake. Yeah, I think this is correct. Okay. All right, any questions about this one? Any questions? Any questions? No questions? Okay, is it okay for me to clear this? Let me do that, and let's see what's next. Okay, now this one is asking for the percent ionization of this acid, which is acetic acid, and it gives a molarity. So the percent ionization, of course, is what we were talking about. It's the same thing as the percent dissociation, all right? So let's see here. Again, you can set up an ice table to represent the dissociation of this acid. Initially, you're gonna have 0.015, 0 here, 0 here. The change here will be minus x plus x and plus x. So at equilibrium, you're gonna have 0.015 minus x. Here you're going to have x, here you're going to have x. Ka will be equal to x squared over 0.015 minus x. And again, we're going to equate that to 1.8 times 10 to the minus 5. And then we can assume again, like before, that x is much less than 0.015. So therefore, this simplifies to x squared over 0.015 is equal to 1.8 times 10 to the minus 5. And then we can solve for x, which would be equal to the square root of 0.015 times 1.8 times 10 to the minus 5. And let me see what that gives. 0.015 times 1.8 times 10 to the minus 5. And let me find the square root of that. So according to my calculation, the answer is 5.2 times 10 to the minus 4. Right? And therefore, this will be equal to the concentration of H plus. And then we find the percent dissociation, which will be equal to the concentration of H plus, which is 5.2 times 10 to the minus 4 m, divided by the initial concentration, which is 0.015 m, times 100%. So let's see what that gives. 5.2 times 10 to the minus 4, divided by 0.015 times 100. And according to my calculation, this works out to be equal to 3.5%. And that's how that is done. All right. Any questions about this one? Any questions?
So is the percentage ionization not any different from the percentage dissociation?
I'm sorry, what's that?
I said, is the percentage ionization not any different from the percentage?
It's the same thing.
Okay.
Those two different, terms to represent the same thing. Okay, any other questions? Any questions out there in Zoom? Okay, let me clear this and move on to the next question. Okay, I'm going to leave this one for you to do. If you understood what we did in A, then B part is very similar. The only difference is that it's a base, right? So in this case, you'd have to do pretty much everything that we did in the A part, but the X value that you're going to solve will give you the concentration of OH minus, and then from that you can find the POH, and then from that you can find the pH. All right, so I'm going to leave that for you to do. If you have any problems doing these, please feel free to contact me. I'll be more than willing to help you out, all right? Let me see what this one says. Calculate the pH of the following. Okay, so you should be able to do this one as well. 11A. they gave you the Ka value, they gave you the molarity, and they're asking for the pH. So that is very similar to what we did earlier. So that's A, let me see B. Okay, let me do B for you because B is a bit different. B has to do with a salt of a weak acid, all right? So in this case here, they gave you 0.055 m sodium cyanide, right? And they gave you the Ka value for hydrocyanic acid, okay? So this is how we would go about solving this one. The first thing you should recognize is that sodium cyanide will undergo complete dissociation. So I'm just going to do this up here. NaCN will undergo complete dissociation to form Na plus Cn minus. Now here's the thing. The Na plus will not interact with water to change the pH, right? Because sodium ions are very stable. But the cyanide ion will act as a base to form HCN plus OH minus, right? So this is the reaction that will take place that will produce hydroxide ions. So therefore, without doing any calculations, we can tell that the pH here would be greater than 7 because hydroxide ions will be formed, right? So we set up an ice table, and the ice table would be basically going to have this equation at the top of the table. So you're going to have Cn minus plus H2O to form HCN plus OH minus. And initially, the concentration of Cn minus is going to be 0.055 because the Cn minus will come from the sodium cyanide. We don't need to concern ourselves with water, but here, this will be 0 and this will be 0. So the change here, because the reaction will be shifting in that direction, the change for the cyanide will be minus X, the change for the hydrocyanic acid will be plus X, and the change for the hydroxide ion will be plus X, right? So therefore, at equilibrium, you're going to have 0.055 minus X here. Here, you're going to have X, and here, you're going to have X, right? So we can write down the equilibrium expression for this. Now, because cyanide here is acting as a base, we can write down the Kb expression for this equation, right? And Kb would be equal to the concentration of HCN times the concentration of OH minus divided by the concentration of Cn minus, right? And then we put in these terms into this equation. You're going to end up with X squared over 0.055 minus X, and that would be equal to Kb. Now, here's the thing. We don't know what the Kb value is directly, right? In fact, even the table I showed you earlier, that you'll have access to doing your test, that table will not have the Kb value of the Cn minus. However, you're given the Ka value of the cyanic acid or the hydrocyanic acid, right? And there is a relationship between Ka and Kb. There's a relationship between Ka for an acid and Kb for the conjugate base of that acid. Now, can anybody tell what that relationship is? There's a relationship between, feel free to look in your notes or text or whatever. There's a relationship between Ka for an acid and Kb for the conjugate base of the acid. Can anybody tell what that relationship is? Can anybody tell me what the relationship between Ka for an acid and Kb for the conjugate base of the acid? Does this look familiar? Kw is equal to Ka times Kb. That's a relationship between the dissociation constant of an acid and the dissociation constant of the conjugate base. And Kw is, of course, the ionic product of water, which is 1.0 times 10 to the minus 14. All right? So we don't know what the Kb is for this particular conjugate base, but we know the Ka for its corresponding acid. So basically, we can write down here that Kb is equal to Kw divided by Ka, right? So therefore, Kw divided by Ka is equal to 1.0 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10. So 1 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10. And according to my calculation, let me do this again. I think I did something wrong here. 1 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10. Okay, so okay, so I got 2.0 times 10 to the, oh, I did do something wrong here. Let me do this one more time. I'm sorry. 1 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10. What am I doing incorrect here? Something is off here. Okay, so this is going to give you 2.0 times 10 to the minus 5. All right, so that would be equal to x squared over 0.055 minus x. Again, we make the assumption, we assume that x is much less compared to 0.055. So therefore, that means that this will simplify to x squared over 0.055 equals to 2.0 times 10 to the minus 4. So that means that x will be equal to the square root of 2.0 times 10 to the minus 4 multiplied by 0.055. And let's see what that gives. So 2 times 10 to the minus 4.
Wouldn't it be 10 to the minus 5? 2.0 times 10 to the
Oh,
minus
the minus 5. Yes, thank you. It should be minus 5. Thank you. Okay, so let me correct that. 2.0 times 10 to the minus 5 times 0.055. And then I find the square root of that. So when I found the square root of that, I got 1.0 times 10 to the minus 3. All right? So that would be x, which would be equal to the concentration of OH minus. Okay, I need to do some erasure here to, you know what, let me erase this here, because I'm going to need some space. Okay, so let me draw a line here to avoid confusion. All right, so basically the concentration of OH minus, or let me just put here, this would be equal to the concentration of OH minus. So we need to find the percent dissociation like before, because we need to make sure that the assumption we made is valid. So the concentration, to get the percent dissociation, we divide the concentration of OH minus by the concentration of the CN minus, and that would be 1.0 times 10 to the minus 3 m divided by 0.055 m times 100%. And let's see what that gives. Okay, times 100. Okay, so I got 1.8%, which is obviously less than 5%. So therefore, assumption is valid. So therefore, we can say that the concentration of OH minus, we're gonna go with that value being equal to 1.0 times 10 to the minus 3 m. So to get the pH, we find the pOH first, which is minus log of 1.0 times 10 to the minus 3, and I can tell that this is going to be equal to 3.00, which means that the pH is equal to 14.0 minus 3.00, which would be equal to 11.00. 11.0. All right, I hope this is not too confusing. Let me just erase this part here. Okay, so that's basically how that is done, all right? Any questions? Any question about this? Any questions? Okay, let me do a quick check as to who came in late. Let me see here. Is Pilgrim here? Yes, Pilgrim is here. Ray, is Ray here? I don't see Ray. Okay. All right. So let me go back to sharing my screen and scrolling down. Okay, so I'm gonna leave the C part for this question, which is number 11. Again, if you have any questions concerning that part, feel free to come and see me, or we can link together on Skype. I mean, not Skype, what am I saying? Zoom. And let me see, D, again, you should be able to do that one. And let me see here, you should be able to do number 12 as well. In fact, number 12 is very easy. And for some reason, I repeated this question, so ignore number 14. 14 is the same as, I think, number 1, if I'm not mistaken. So you can ignore number 14.
Is there no question 13?
I'm sorry?
I said, is there no question 13, or do you also want us to do that one ourselves?
Oh, there's no question 13. Okay, so there's no question 13. Let me see here. Question 15. All right, now in the case of question 15, you should be able to do it, but there's one thing I need to say about this. Basically, what this question is asking for you is to find the pH of a solution made up of these two acids, and they give you the concentrations and your Ka values, right? So the approach that you would take in order to solve this one is that you work out the concentration of H plus for each of them, right? So you figure out the concentration of H plus for the lactic acid, and then you do the same process for the propanoic acid. And then you add those two together and then find the minus log of that to get the pH. You see what I'm saying? So you work them out separately, right? To get the concentration of H plus from each of those acids, add them together, and then you find the minus log of that total to get the pH of that solution. And that's pretty much how you approach question 15. Again, if you have any problems while doing it, please let me know. Let me scroll down here. Okay, let's look at this one here. I'm going to do this one. I think I did an example in the video lecture, but let me go ahead and do this one anyway. Okay, so this has to do with a diprotic acid. A diprotic acid is basically an acid that releases, is capable of releasing 2 hydrogen ions for every molecule of the acid, right? So for the sake of abbreviation, I'm just going to call this acid, H2A. All right? So the question is asking, what is the pH of a 0.10 m solution of this acid? And it gives you the Ka value associated with each dissociation, right? So basically what they're saying here is that for the first dissociation, to give H plus and HA minus, the Ka1 value is equal to 7.9 times 10 to the minus 5. And then this Ha minus will itself react to form H plus A2 minus, right? So the this is Ka1 for the first dissociation, and the Ka2 for the second dissociation is 1.6 times 10 to the minus 12, right? So this is what happens in a lot of cases where you have an acid that can release more than one hydrogen ion, right? Now, because this is H2A, this question is asking, well, first it's asking for the pH, and then it's asking in the second part, the concentration of this, which is the A2 minus, right? Because this is formed when the original acid loses two hydrogen ions, all right? So let's focus on firstly, the first part, and that is what is the pH of a 0.10 M solution of this acid. So I need to erase this bottom part here so that I can set up the ice table for this one. So in this case here, we're going to start off with initially the concentration of the original acid is 0.10. This would be 0 and this would be 0. The change here would be minus X plus X plus X respectively. And therefore at equilibrium, we're going to have 0.10 minus X. Here we're going to have X and here we're going to have X. So Ka1 is equal to the concentration of H plus times the concentration of Ha minus divided by concentration of H2A, all right? So when we put these terms into this equation, you're going to end up with X squared over is equal to X squared over 0.10 minus X. I'm sorry, 0.10. That's what should be down here. 0.10, which is equal to 7.9 times 10 to the minus 5, right? This implies that X will be equal to the square root of 0.10 times 7.9 times 10 to the minus 5. So let's see what that gives. Well, 1 times 7.9 times 10 to the minus 5 square root. Okay, so I got, and please correct me if I'm wrong, but I got 2.8 times 10 to the minus 3. All right? And that would be equal to the concentration of H plus. So the next step is to find the percent dissociation like we did before. And that would be equal to 2.8 times 10 to the minus 3 M divided by the initial concentration, which is 0.10 M times 100%. So let's see what that gives. 2.8 times 10 to the minus 3 divided by 0.1 times 100. And according to my calculation, I got 2.8%, which is less than 5%. So therefore, the assumption will be valid. So assumption is valid. All right? So basically, because the assumption is valid, we can assume that that same assumption would be valid for the second dissociation, right? So therefore, we can basically, because remember, there's another dissociation that can potentially take place, where the Ha minus react with water, right? To form H3O plus and A minus. That's a second dissociation. But because this first dissociation gives a concentration of H plus, which is very small, the second dissociation will give a concentration of H plus, which will be even smaller, right? Because, and I don't know if I'm quite sure I mentioned this in the video, whenever you have the potential of more than one dissociation taking place, the subsequent dissociation would be smaller compared to the previous dissociation. So the first dissociation will be the strongest, the second dissociation will be weaker, and if there's a third dissociation, that will be weaker and continue, right? So therefore, we don't need to look at the second dissociation to see if any H plus will be produced. So therefore, all we have to do from here is say that because the concentration of H plus is equal to that, let me do it up here, the pH would be equal to minus log of the concentration of H plus, which is 2.8 times 10 to the minus 3. So let's see what that gives. So 2.8 times 10 to the minus 3 log minus, okay, so I got 2.55. So that would be the answer to the first part, which is asking for the pH of the solution. Now the next part is asking for the concentration of the A2 minus. Let me just do a quick, okay. So the next part is asking for the concentration of the A2 minus. So basically, I need to clear this. So is it okay for me to, okay. So let me clear this. Okay, now remember, the A2 minus, which is this right here, is formed when HA minus undergoes dissociation to form A2 minus plus H plus, right? So, and the Ka value for this, which is Ka2, is equal to 1.6 times 10 to the minus 12, right? So, based on this equation, we can say that Ka, oh, before I do that, let me do the ice table for this here. So, in the case of this reaction right here, the final concentration of H plus would be equal to the initial concentration of H plus in this case, which is 2.8 times 10 to the minus 3, right? And the final concentration of HA minus from the previous dissociation would be the same as the initial concentration of HA minus in the second dissociation. So that's also going to be 2.8 times 10 to the minus 3, right? So initially, you're going to have 2.8 times 10 to the minus 3 for the A minus, 2.8 times 10 to the minus 3 for the H plus, and 0 here, right? The change here would be minus X plus X plus X. So at equilibrium, you're going to have 2.8 times 10 to the minus 3 here, minus X. Here you're going to have X, and here you're going to have 2.8 times 10 to the minus 3 plus X. And therefore, we can write down the expression for Ka2, which is equal to the concentration of A2 minus times the concentration of H plus divided by the concentration of HA minus. And before we even do that, let me just say that, as I said before, the second dissociation would even be weaker than the first dissociation. So what that means is that we can assume that X is very small. So what that means? That means that X would be approximately 0 compared to 2.83, 2.8 times 10 to the minus 3. So basically we can reduce this to 2.8 times 10 to the minus 3. We can reduce this to 2.8 times 10 to the minus 3. We're still going to have X here, right? So we're going to put in these terms, the 2.8 times 10 to the minus 3 here and here, and the X value here. So for the A2 minus, you're going to have 2.8 times 10 to the minus 3. For the H plus, that would be, for the H plus, that would be 2.8 times 10 to the minus 3. For the A2 minus, that would be X. And for the HA minus, that would be 2.8 times 10 to the minus 3. And these two will cancel out. So therefore, Ka2 would be equal to X, which would be equal to 1.6 times 10 to the minus 12, which would be equal to the concentration of A2 minus. Concentration of A2 minus. And that's it. That's how we get that answer. All right? Okay, any questions about this one? Any questions? Questions? Any questions? Any questions out there in Zoom? All righty. All right, let me clear this here. What time is it? Okay, we have about 18 minutes left. All right, let me clear this here. And scroll down. Okay, all right. This question is saying, calculate the pH of a solution that results when 40 mils of a 0.10 m ammonia solution is diluted with 20 mils of distilled water. Okay, I'm very interested in hearing what you guys have to say about solving this one. So you're starting off with 40 mils of a 0.10 m ammonia solution, and you're diluting it with 20 mils of distilled water. Let me just say that you're going to need the KB, which, if you look it up, is going to be 1.8 times 10 to the minus 5. All right. So if you look it up in the table that I mentioned earlier, that's it. So you're going to need that. So let me hear what you guys have to say about this particular problem. How would you solve it? What do you think the very first step you need to take in solving this problem?
Write out the equation.
Hmm?
Write out the equation so you can make the ice table.
Talking about the reaction of the ammonia?
Mhm.
Well, you will need to do that, but before you do that, there's something you need to do. You're right about that, but not initially. There's one important step. Oh, let me see what this person is saying. Find the concentration of ammonia after dilution. Who said that? Let me see who said that. Oh, Mr. David. That's indeed correct. You need to find the molarity of the ammonia after dilution. So how would you go about doing that? See, somebody's saying something. Mr. David again. He said using the formula C1 V1 is equal to C2 V2. And again, I would agree with him. You remember the dilution equation, right? So, how would you use this equation in this particular case? What would be C1, what would be V1, what would be C2, what would be V2?
Wouldn't it be 40 millimeters times 0.100 moles of concentration equals 60 millimeters?
Exactly,
times-
right. So based on what you're telling me, this would be C1, this would be V1, and V2 would be 60, which would be 20.0 mils plus the original 40.0 mils, right? So that would be 60.0 mils. So as you correctly said, you want to find C2, right? So C2 would be C1 V1 over V2. C1 is 0.100 m times V1, which is 40.0 mils.
Lagging on the screen, like it's not showing what you're writing.
I'm sorry?
I said it's, oh, there we go. It wasn't showing what you were writing, but now it did.
Oh, yeah, there's some lag between, and I just see something saying that your internet connection is unstable. So sorry about that. And then the total volume is 60.0 mils. All right. So I think I did this one. So this gives you 0.0667 m. All right. Okay, very good. So that's what we need to do before we do anything else, right? What's the next step? Now that we have the molarity of the diluted solution, what will be the next step? What did you say earlier?
We need to find the reaction and then create the ice table.
All right, so it's NH3 plus H2O to form NH4 plus OH minus, right? So initially, the concentration of the ammonia is what we just calculated here, which is 0.0667. Here, you're gonna have 0, and for the OH minus, you're gonna have 0. The change here is minus X plus X plus X. So therefore, at equilibrium, you're gonna have 0.0667 minus X. Here you're gonna have X, here you're gonna have X, right? Okay, so again, I'm gonna need some space. Let me just erase this top part right here. Okay, so we can write down the KB expression. KB, because it's a base, that will be equal to X squared over 0.0667 minus X. We assume, again, that X is much smaller compared to 0.0667. So that this part here becomes X squared over 0.0667. And that would be equal to 1.8 times 10 to the minus 5, which is a KB value. So therefore, X will be equal to the square root of 0.0667 times 1.8 times 10 to the minus 5. So 0.0667 times 1.8 times 10 to the minus 5. And then I find the square root of that. So when I did that, I got 1.1 times 10 to the minus 3. Right? And that would be the concentration of OH minus, right? And what's the next step after that? Now that we have the concentration of OH minus based on the assumption, what do we do next?
You find pH.
Before you do that,
We need to do the percentage.
percent dissociation. And let's hope it's less than 5%. I think it is. Percent dissociation is 1.1 times 10 to the minus 3 divided by the initial concentration, which is 0.0667 mm times 100%. Yeah, I think this is less than 5%. 1.1 times 10 to the minus 3 divided by 0.0667 times 100. So this is 1.6%, right? Which is less than 5%. So therefore, assumption is valid. So therefore, as you were just saying, you find the POH, which is minus log of 1.1 times 10 to the minus 3. Let's see what that gives. 1.1 times 10 to the minus 3 log minus, okay, so I got 2.96, right? Which means that the pH is equal to what?
13 minus.
14.00 minus 2.96, right? And that gives a value of 11.04 as the final answer. All right? Any questions about this one? Any questions? Okay. Let me clear this. We might not be able to do the next one in the time that we have left. Let's see. Okay, you know what? Let me see. How many questions do we have left? Okay, we only have 2. Okay. I'm going to stop here for today because we won't have time to finish the next one. All right? You can try it on your own if you so choose, but we're going to start with that. And I don't remember, did I publish the modules for the next chapter? Let me see. No, I didn't. So what I'm gonna do is publish that right now, so you can get started on watching that. All right, and the next chapter is basically an extension or a natural progression from what we were just discussing. Okay, so let me see here. And it's relatively long, right? So, and the reason why it's relatively long is because I took some time to do some examples. You see these here, pH calculations, these are all examples, and I want you to go through them because it's very important for you to do these type of calculations when it comes to acid-base titration. All right, so just take your time to watch the videos and try to understand as much as possible. And again, if there's any part of that you're having difficulty with understanding, again, feel free to contact me during my office hours so that I can explain to you what's going on there. Unfortunately, this is one of those chapters where, well, the chapter that we're doing now and the next chapter, I would say those are the two longest chapters. And the reason why is because you have to know how to do the calculations for different situations. All right. So unfortunately, that's just basically how these chapters are. All right. Okay. That's pretty much it, unless there are any questions. Yes, ma'am.
So do you know when the time frame for test 2 would be? Because according to the syllabus, it says March 9th, but like I know we've had a lot of setbacks.
Yeah, right. So yeah, because of the setbacks, I have to basically put that off the test number 2. And we just completed, let me see here. So you were tested for the first 2 chapters, right? And then we have equilibrium, and then we have this. So I would probably schedule the test for, if not next week, the week after. And I think I'm more inclined to give you the week after because this particular chapter that we're in, as you can observe, is a bit heavy in terms of the math. So you probably need more time to review and understand and so on. So I'm inclined to put that test off until week after next, just to give you time to, well, first to give me time to grade it and then send back the graded assignment to you and you can have that to review, all right? So I think tentatively that's a plan. All right? All right, so folks, that's it for today. I'll see you guys next week, right?
Is next week spring break or is it the week after?
Oh, good question. Let me see if I can find the schedule here. That's a good question, sir. Okay, where would I find the academics? Okay, so this is the calendar here. And spring break is 16th to the 22nd. 16th, next week actually. So the test would have to be the week after. Yeah. And hopefully by then, we can move into our offices upstairs.
Is your office upstairs? So is there like somewhere else that you're holding your office hours?
Well, I just found out that that I can use the adjunct offices over there in the math department. I haven't used it yet. I'm thinking of going over there today, but so far, basically, I've been using my home. Or I use my office over in the Citrus campus when I'm there. Yeah, this is a bit of a annoying inconvenience. All right, let me sign over this here.
Thank you.
All right, take care. All right, you guys out there in Zoom, I'm signing.